I'm gonna make this short video that is a bird's eye view of Galois theory. Like I said, it's a bird's eye view, so um, I want to gloss over a lot of detail. So this video is really meant for people who already know a little bit of Galois theory, and they're just watching it as a review, or for beginners who want to have a very rough idea. Um, like I said, it's a bird's eye view. I want to be faithful to the original mission of Galois and solve the traditional issue of finding a general solution to a polynomial equation. Okay, so please, I'm not gonna talk about field theory that much. A lot of details I'm gonna skip because, like I said, I'm trying to keep this as short as possible. Just a quick warning, I'm a very dumb guy, so I really dumb things down a lot because that's how I understand. If I make any mistake or if something is just completely incorrect, please put something in the comments. I'm not a researcher. I'm just a regular guy who studied math. So please, if I make any any mistakes, let me know. If you'd like more videos like this, just please leave a comment, put something there, and I'll read it. Thank you. I'm gonna read all your comments. Thank you. So first of all, let's start. What do we mean by a solution to a general polynomial equation? That means we want something like x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a, right? So we want our solutions to just simply be a result of adding, subtracting, multiplying, dividing rational numbers and the coefficients, and also taking square roots, nothing more. All right? And we want it to be general. By general, we mean that we don't have repeated roots. Okay, we want every root to be unique. Okay, so let's begin. So first of all, a general polynomial is just the product of x minus the roots of that polynomial. Okay, so so a general polynomial can be written as g of x is equal to x to the power of n minus s1 times x to the power of n minus 1 plus or minus all the way up to the constant term, which is negative 1 to the power of n times Sn, where all these s's are the coefficients, and the coefficients you can write them in the following way. So let's just immediately jump into an example. Now, why are the coefficients given the letter s? We're going to understand that in a bit. The s stands for elementary symmetric polynomials. Like I said, an example will clarify all of this. So let's try a polynomial that we already know the solution to. So x minus 2 times x plus 3 times x plus 4. Of course, if you expand this, you're going to get x cubed plus 5x squared minus 2x minus 24. But now let's try to do it in the way that's stated above. So we know that the first root is 2, the second root is negative 3, and the third root is negative 4. So our alpha 1 is 2, our alpha 2 is negative 3, and our alpha 3 is negative 4. Now to find S1, what you have to do is the summation of all the roots. So it's alpha 1 plus alpha 2 plus alpha 3, which is 2 plus negative 3 minus 4, which is negative 5. Alpha 2 again is the sum where I is less than j of alpha j times alpha I times alpha j. So what you get is the following. Again, please pause it. I'm not going to go through all the details, but you get negative 2. And then alpha 3 is just simply the product of the three roots, which you get 24. Now the general form of the polynomial is right over here. So now we're just going to fix our sign. So x cubed minus negative 5 plus negative 2x to the power of 1 minus 24. We want our leading coefficient to be 1, right? Because remember, we're in the field of rationals. Like I said, I don't want to really talk about field theory, but it's pretty simple. Just always have the leading coefficient equal to 1 by division. So finally, we get the answer. Okay, so that's just a general method. Here's the interesting thing. Here's where the fun begins. So a polynomial p of alpha 1 all the way to alpha n, where alpha 1 to alpha n is symmetric if it remains unchanged when you permute the variables. And the very interesting thing that you notice is if you, for the elementary symmetric polynomials, if you switch the roots around, your answers will be the same. So for example, do it yourself. If you let alpha 1 equal -3 and alpha 2 equal 2 and alpha 3 equal -4, you will also get the same answer. Now, why is that? Because you see, um, you could have written this g of x as x plus 3 times x minus 2 times x plus 4. That wouldn't have changed anything. Your coefficients would have stayed the same. Or you could have written g of x as x plus 4 times x minus 2 times x plus 3. Again, you wouldn't have changed anything. So they're called elementary symmetric polynomials, these coefficients, because they are symmetric, right? If you switch them around, if you switch the roots around, the coefficients stay the same. So each elementary symmetric polynomial is a symmetric polynomial of the roots. So it follows that any polynomial in the coefficients of g of x is a polynomial of the roots. And now here is where the genius of Newton comes in. He actually proves the converse. I'm not going to go through the proof. It's a bit lengthy, but it's not really difficult. I said, like, this is going to be a bird's eye view, so I'm not really going to do all the proofs. So any symmetric polynomial in the roots of p of x is a polynomial in the coefficients. So any polynomial that's symmetric in the roots. So that means if you permute the roots around, the polynomial stays the same. What you could do is you could write it as a polynomial in the S1, S2, S3, and so on. So he did the converse. He proved the converse. All right, so great. So a polynomial p of alpha 1 all the way to alpha n is symmetric if and only if it is a polynomial in the elementary symmetric functions S1 to Sn. So any polynomial that's symmetric in the roots is symmetric in the coefficients. Okay? And here is even a more interesting part. If p of t1 to tn has integer coefficients, then so does q of s1 to sn. Okay, so now maybe this has a little bit of field theory to it, but it's not that difficult. The set of symmetric polynomials in the roots of a polynomial p of x is the same as the set of polynomials in the coefficients of p of x. In particular, any symmetric polynomial in the roots of p of x belongs to the same field as the coefficients. Okay, so if p of x is a polynomial over the rational numbers, then any symmetric polynomial in the roots of p of x belongs to q. Okay? So when trying to find the roots of a polynomial, we can assume that any symmetric polynomial in the roots is known. Why is that? Because there's actually an algorithm for computing the symmetric polynomials of the roots, which requires only knowing the coefficients of the polynomial. So we can write the roots in terms of the coefficients, which is exactly what we want. So if you have a symmetric polynomial in the roots, there's an algorithm in which you can write these in terms of the coefficients of the polynomial. Okay, so now we'll see how this is going to help us. So now we're going to jump into something a bit different. It's called the roots of unity, but we'll see how this applies to solving polynomial equations. So roots of unity are pretty simple. So it's just the nth roots of unity are the complex solutions to the equation x to the power of n is equal to 1. And there are n solutions to the equation. So for example, let's say n is equal to 2. So x to the power of 2 is equal to 1. What are the two solutions to this? Obviously 1 and -1. Well, what about if we go higher than 2? So let n be a positive integer and u of n be the set of nth roots of unity. Then u subscript n, these are the roots of unity, is e to the power 2k pi I divided by n, where k is an element of the set 1 to n. So let's do an example immediately. So what are the three roots of unity? Well, these are the solutions, where if I plug them into x and I cube them, I should get 1. Well, with a little bit of thinking, I mean, immediately you know 1 is a solution, But with a little bit of thinking, you're going to get that x is equal to negative 1 plus I square root of 3 divided by 2, and negative 1 minus I square root of 3 divided by 2. And now we can write the set of the three roots of unity as I, comma, negative 1 plus I square root of 3 divided by 2, comma, negative 1 minus I square root of 3 divided by 2. But here's the thing, there's an even easier way to do it. And that is you have this circle, unit circle in your complex plane, and you want to divide it into three parts. So obviously three equal slices if you want to think of it like that. To go from 1 to the first root of unity, you have to rotate by 2 pi I divided by 3. So your first root of unity is e to the power of 2 pi I divided by 3, right? Which is right over here. Okay, so k is 1 and n is 3. So that's your first root of unity. So you could write it in a different way. And now to go to your second root of unity, again, you're going to rotate by 2 pi divided by 3, and then you get your second root of unity, which is e to the power of 4 pi I divided by 3. And then finally, if you go another 2 pi over 3, you're back to 1. So these are your three roots of unity. All right, so I hope that made sense. It shouldn't be that difficult. So solutions to polynomial equations for degree 2 were found a really long time ago. I think the Babylonians already figured that out. The cubic, the same idea, but the proof was geometric. I think the person who figured that out, who did the geometric like proof, is Al-Khwarizmi, if I'm not mistaken. And then but then that was a geometric solutions, but the people who really discovered algebraic solutions to cubic polynomial equations were the Italians, right? There are these really nice stories about, you know, math duels and the lore of solving polynomial equations, right? But I'm gonna skip that and just like jump into Lagrange's method. Now, what Lagrange did is that he actually studied all the solutions. Also to cubic, I'm sorry, also I think the Italians solved quartics too algebraically. And Lagrange studied these in detail. And what Lagrange did is that all these solutions were ad hoc. Lagrange figured out a systematic way, a methodical way of solving polynomial equations. Okay, and then what he determined is the following, is that in each case the determination of the auxiliary equation, so he devised an auxiliary equation um, of the construction of an expression in the rational in the roots. Okay, so you need to create an auxiliary equation which is of lower degree than the original. By his exhaustive examination of the known cases, Lagrange laid the groundwork for the construction of the general theory. In all of Lagrange's solutions, an auxiliary equation called the resolvent was used. The resolvent has a lower degree than the original polynomial. Okay, now what is the resolvent? So let alpha 1, alpha 2, and so on be the roots of the degree and polynomial, and omega 1, omega 2, and so on be the roots of unity, or the roots of x to the power of n is equal to 1. Now the Lagrange resolvent is defined to be so u, v, whatever you want to call it. So the first one, let's say, is u is equal to alpha 1 times omega 1 to the power of 0 plus alpha 2 times omega 1 to the power of 1 plus alpha 3 times omega 1 to the power of 2, and so on. And then the next one would be, let's say, v, which is equal to alpha 1 times omega, alpha 1 times omega 2 to the power of 0 plus alpha 2 times omega 2 to the power of 1 plus alpha 3 times omega 3 uh, to the power of 2, and then the one after, and so on. Okay, so you're just really changing the subscript 1 over here in every case. So it's going to become 2, and for the one after that's going to become 3, and then 4, and so on. Okay, so now let's try to apply Lagrange's method. Of course, I'm not going to do this for all of them because it's the same idea, but it just becomes really algebraically tedious. So let f of x be x squared plus bx plus c, where b and c are elements of k. K in this case is going to be the rational numbers. and alpha 1 and alpha 2 are the roots in some extension field K. Again, yeah, so our K, yeah, so okay, yeah, so the base field is Q, all right? And then we're going to extend the field. I should have tried to avoid using, like I said, I'm trying to not go into field theory that much. So now we can write, so we know that the roots are alpha 1 and alpha 2. So now if we expand, we get x squared plus bx plus c is equal to x squared minus alpha 1 plus alpha 2x plus alpha 1 times alpha 2. And then now just comparing, we get that alpha 1 plus alpha 2 is equal to negative b, and alpha 1 times alpha 2 is equal to c. Now let's go back to our resolvent right over here. Now the resolvent is going to be, so our first resolvent, we're going to call it u. It's going to be alpha 1 times omega 1 to the power of 0 plus alpha 2 times omega 2 to the power of 1, right? But the first root of unity of x squared is equal to 1 is just 1. So 1 to the power of 0 is 1, and 1 to the power of 1 is 1, so we just get alpha 1 plus alpha 2. Okay, now the next resolvent v is going to be alpha 1 times omega 2 to the power of 0 plus alpha 2 times omega 2 to the power of 1. Now remember, omega 2 is negative 1. So that's just going to be alpha 1 minus alpha 2. But alpha 1 plus alpha 2 is just negative b. And now v, unfortunately, we want to try to sort of link it, right? What do you notice immediately? Immediately you can apply Newton's theorem, right? So alpha 1 plus alpha 2, if you switch the roots around, it's not going to affect it. U is always going to be negative b because this is symmetric with respect to the roots. However, v is not symmetric. Switching alpha 1 and alpha 2 has an effect. The effect is that v will just become negative. How do we make v symmetric? Because remember, once alpha 1 minus alpha 2 or v is symmetric, we know from Newton's theorem that there's an algorithm to write it in terms of the in terms of the coefficients. Well, squaring it does the trick, right? So once we square it, we get alpha 1 squared minus blah, blah, blah. So you guys do the algebra, right? Well, what you're going to figure out is that alpha 1 plus alpha 2 squared minus 4 times alpha 1 times alpha 2 is b squared minus 4c. Remember, in all our cases, we're taking a to be 1. So you see, this is just Newton's theorem at work. So we get v squared is just b squared minus 4c. And now we're going to take this, right? We know that alpha, now if we work with u and v, right? Yeah, so if we add u to v, after all the dust settles, you're going to get that alpha 1 is equal to 1 half u plus v, and alpha 2 is 1 half u minus v. So just play around, tinker around with these two, right? I recommend a separate sheet of paper and try working these out algebraically. But we know what u and v are, right? So we just plug in u is alpha 1 plus alpha 2, v is the square root of b squared minus 4c, and then you're going to get the solutions that you've known since high school. Okay, now what about the cubic? Like I said, it's the same basic idea, but it's very exhausting, okay? Same thing, this is the general, x cubed plus bx squared plus cx plus d. Okay, you can break it down as x minus alpha 1, x minus alpha 2, x minus alpha 3. And here is something that's really helpful. You could, I think this is called the Chern transformation, Chernhouse transformation or something, but you could always depress your cubic, right? If you use the translation x is equal to y minus b divided by 3, again, I'm not going to prove this, but you could do it, so please Google it. So now you can rewrite this f of x as g of y, which is y cubed plus py plus q, okay? And then now we're going to try to solve the depressed cubic, but then we always know that we can go back, right, because we know that y is just simply x plus b over 3. So you could solve for x, all right? And now here, once again, you see you're going to do some algebra, but then once again you see that you're going to use the resolvent, okay? Correct? So your first resolvent, again, the same basic idea, except in this case we're going to have a coefficient of 1/3. Why is that? Because it simplifies the algebra. Okay, so we have alpha 1 plus omega alpha 2 plus omega squared alpha 3. So if we, yeah, so you have these, again, go back right over here, right, and then apply this rule. Remember, the first thing, you're just going to get the sum of the three roots because omega 1 is always 1. But then I skipped that step, right, because it's trivial. Your second resolvent and your third one are the ones that are of interest. And remember the relationship that um, omega cubed, so any root of unity there, if you cube it, you should, so you're just going, yeah, so remember what the relationship is that if you do omega, here I think I called it phi, but like, yeah, so these you could think of them as omega, so maybe I should have just changed the variables, but the names I mean, but that's fine, right? Because omega squared, so if you square this, you jump over here. If you cube this, you're going to go 1, 2, 3 back to the point, right? So don't forget these relationships. If you notice, these are sort of like cyclic. So please keep that in mind when you're simplifying and doing your resolvent, okay? Keep those ideas in mind. So these are your two resolvents, right? This equality, again, is just algebra. And then what you realize is the following, that when you cube the u's and the v's, okay, at some stage you're going to cube the u's and the v's, and then what you get is the following, is that u cubed plus v cubed is negative q. So again, you get that they're symmetric with respect to switching the roots around, okay? So that means you can write them in terms of the coefficient. And then after a lot of tedious algebra, right, you get the solution. So the first root is this, the second root is this, the third root is this. And what you notice is, if you look at the radicals, what you notice is you have roots of unity. So they're identical up to roots of unity. And this is going to be very interesting to us. So this should be the third root, sorry. Same idea with the quartic. Again, with the quartic, it's the same basic idea. I recommend you go through it by yourselves, but it's the same thing. You're going to use resolvents and so on. I want to talk, so I even stopped at some point and I'm like, whatever, I'm not going to continue this because it's just tedious algebra. Now I want to talk about the big picture that you see. In the quadratic case, v squared is closed under the permutation of roots. So this is the big idea, okay? If you forget all the algebra, just focus on the big idea. V squared is closed under the permutation of roots. So what does that mean? That means it's a symmetric function of the roots and the rational function of the coefficients, right? If you switch the roots around, v squared does not change in the quadratic case. So that means we know that it's a rational function of the coefficients. In the second case, u cubed and v cubed is closed under the permutation of roots, right? So closed under the permutation of roots means if we permute the roots, u could switch to v and v could switch to u, that's okay. But what doesn't change? What doesn't change is the following. What doesn't change is u cubed plus v cubed and u cubed times v cubed, which we used to solve the cubic. Again, in the quartic case, u to the power of 4, v to the power of 4, w to the power of 4, again, is closed under the permutation of roots. So what does that mean? That means a cubic with u to the power of 4, v to the power of 4, and w to the power of 4 can be created to solve it. So maybe I worded it better right over here. So you see the quadratic u is equal to alpha 1 plus alpha 2, which is just negative b. V is not symmetric, right? If we permute the roots, we get a negative value, but we squared it. Okay, what about the cubic? So our v and our u were the following. Then what did we do? When we cubed them, that set of u cubed and v cubed is symmetric, right? Is closed. So when we permute the roots, u and v switch values. That's okay. U and v could switch values. But what's the idea? Is that u cubed and v cubed is closed under the permutation of roots. So what does that tell us? So we can write a polynomial of lower degree, which is x squared minus u cubed plus v cubed x plus u cubed times v cubed is equal to 0. And u cubed plus v cubed and u cubed times v cubed is symmetric with respect to the roots. So that means we can write it in terms of the coefficients. Same thing for the quartic. U, V, and W, again, these are symmetric. Sorry, these are closed. When we raise them to the power of 4, they're closed, okay? You could raise them to the power of 4, you could raise them to the power of 2. In this case, I think my resolvent, I chose a sort of different resolvent, an easier resolvent. So squaring them, they remain closed under the permutation of roots. And now what's the idea? Is that we can write a cubic polynomial where u squared plus v squared plus w squared, u squared times v squared plus u squared times w squared plus v squared times w squared, and v squared times v, sorry, u squared times v squared times w squared. These are all, they're going to be symmetric with respect to the permutation of roots, and also that means we can write them in terms of the coefficients. Okay, so again, I hope that was clear. This is very like impromptu, so I hope I'm not confusing everybody. And the great idea is the following. When Lagrange attempted the same method to solve the quintic using the 5 roots of unity, he realized that u to the power of 5, v to the power of 5, w to the power of 5, and y to the power of 5 is not closed under the permutation of roots. In fact, it takes 24 different values upon the permutation of all of its roots. So then Lagrange hypothesized that the quintic is not solvable using the techniques that were employed before. But just because it's not solvable using that technique doesn't mean it's not solvable in general. Abel is the one who proved, Abel and Ruffini proved that it's not solvable. Now, what was Galois' insight? So Galois didn't suddenly burst upon the world of mathematics. His work, startling as it may have been in his own generation, can be seen in hindsight as the natural and perhaps even necessary culmination of centuries of development. According to Galois, if we can solve a general degree n polynomial by radicals, then we should be able to find a sequence of intermediate variables which satisfy lower degree polynomials. Such intermediate variables should be fixed by subgroups of Sn. This is very crucial. This is the very crucial discovery of Galois that establishes the connection between groups and polynomials. So basically, this is what Galois said. In the case of the quadratic, alpha 1 minus alpha 2 squared, or delta squared, is completely symmetric with respect to z2. In the case of the cubic, like we said before, these are symmetric under the permutation of the roots of the under z3 permutation of the roots. Then z squared is symmetric under all permutation of the roots. The idea of the quartic is that the following are symmetric with respect to the Klein 4 permutation of the roots. Q cubed is symmetric with respect to A4 permutation of the roots, and delta squared is symmetric with respect to the Z2 permutation of the roots. So what do we mean? So hopefully this will make sense. So you see, this is for the quadratic case right over here. So delta squared is completely symmetric, right? No matter how you permute the roots, nothing's going to change. You'll get the same value, right? So you can write it in terms of the coefficient. So the coefficients live in this row, right? Because also the coefficients are symmetric with respect to any permutation of the roots. So you only have 2 roots, so Z2 is the group that we're talking about. And then now when you go to the upper row where the roots live, so remember the roots are not symmetric with respect to any permutation because they are the roots, right? If you permute the roots change, of course. And the same thing with delta, which is the square root of delta squared. If you permute the roots, square root of b squared minus 4ac will either be positive or negative. Okay, what about the cubic? Again, the cubic right over here live the coefficients, and what also lives with them is that delta squared. Now, if you take the square root, the only thing that keeps it symmetric, that keeps the square root the same value that it is z3. But also we have a cubic, and the cubic, so if you scroll up over here, you see this u cubed and v cubed. Remember, they're symmetric with respect to z cubed, but they're not symmetric with respect to all the permutations, only those z3 permutations. Okay? And if you take the square root of those, it no longer becomes symmetric with respect to anything. So what you notice is the following. You're like building this tower, and to go from one tower to the next, what you have to do is take either square roots or cube roots or whatever. So you're taking, so to go from here to here, so to go from, so the solutions live on top. To go to the, you want to go all the way down to the coefficients, which are symmetric with respect to everything. The roots are symmetric with respect to nothing, so the identity group, right? So to go from here to here, you're going to have to take, right, you're going to take square roots from here to here, square roots, and then from here to here, cube roots. The same thing with the quartic. So here, S4 live the roots with delta squared. You want to go all the way up to the roots. To go from here to here, you're going to need to take square roots. To go from here to here, you're going to need to take cube roots. And then to go from here to here, you're going to have to take square roots of two different things. Okay? And that's what Galois noticed. So according to Galois, if we can solve a general degree n polynomial by radicals, then we should be able to find a sequence of intermediate variables which satisfy lower degree polynomials. Such intermediate variables should be fixed by subgroups of Sn. And this is the crucial discovery that linked groups with polynomials. Okay, so the basic idea is we want the process of going from one row to the next to consist of only taking radicals. We are able to use radicals to go from one row to the next if we can find a polynomial in one row that is a power of itself. We want to compute a polynomial that is proportional to the original quantity. We want to find those quantities whose permutations are proportional to itself. Since we are working with finite groups of permutations and every permutation in a finite group has finite order, this implies the concept of proportionality has got to be a root of unity. Okay? Like I said, I try to avoid field theory. I try to avoid a lot of technical language, right? Because we can talk about separable, we can talk about extensions, normal extensions, and so on. Like I said, I want this to be a bird's eye view. If you find any mistakes, please, please, please let me know. I'm not going to close the comments. Please comment as much as you want. Put some constructive criticism. I really appreciate that. I would like to do a lot more if I had time and like resources. I would like to do a lot more, but I hope this helps. There's a lot of like very smart people on YouTube, so I really appreciate you watching my video. Thank you very much.